All right, so I'm talking in this video about when the exponent is not a whole number. And I want you to think about a question that is sort of deceiving, and that is what number is halfway between the numbers 1 and 4? And there's sort of multiple correct answers here. One correct answer is that the number is 2.5, because 2.5 is the same distance away from 1 and 4. And I got 2.5 by just adding them up and dividing by 2. That's the mean. That's the arithmetic mean. So that's 1 plus 4 is 5. Divided by 2, you get 2.5. And 2.5 is 1.5 steps away from either side. But an answer that I like more than 2.5 is that the number 2 is halfway in between 1 and 4. And the reason I like that is because instead of adding 1.5 over and over, I can multiply by 2 over and over, and I get from one step to the other one. And that is what we're talking about with exponential growth. So when you have an exponential problem and you're trying to think about fitting a number in between, you want to think about what can I multiply by to get in between there. Well, it also turns out that 2 is the square root of 4. And if you remember your exponent properties, you'll remember that the square root can also be written as the 1/2 power. And this idea of being halfway between in a multiplication problem is where this concept comes from, that you're multiplying by 2 twice to get from 1 to 4. So that's why the number that's halfway in between is the square root. Okay? So we could play a similar game where if we had, say, going from 1 blank blank 27, trying to think of what numbers fit in between there. Well, if I was doing it additively, I would do 1 plus 27 and I'd divide that by 3 and I'd put those numbers in between. But I'm not going to do it like adding. I'm not doing it linear. I'm doing it exponential. So I want to think, what number can I multiply by to get up to 27? In other words, 1 times a number raised to the third power is 27. And why is it raised to the third power? Because I want to go once, twice, 3 times right there. It turns out that this is a nice number that I chose. It's 3. 3, 9, 27, showing me I'm going times 3, times 3, times 3. And this is another nice connection that the cube root of 27 is 3. 27 to the 1/3 power is 3, because 3 is 1/3 of the way up to 27 multiplicatively. But this gives me another nice connection, which I can say 27 to the 2/3 power has to be 9, because that's 2/3 of the way up to 9. So keep this idea in mind that when you are trying to get from one number to another, you can think about what is in between those numbers by using fraction exponents. And fraction exponents are the same as roots. Okay? So that's the big idea, is when the exponent is a fraction, when the exponent is not a whole number, you're thinking of numbers that fit in between with a multiplication pattern. And that is the same concept as talking about square roots or cube roots or fifth roots or 17th roots or anything like that. Okay, I want you to notice something else with these simple examples, and then we'll do one other example with some numbers that I can't do in my head. One other thing I want you to notice is that the difference between the first and the second number is 1. The difference between the second and the third number is 2. So it grows more in the second pattern than it does in the first pattern. It grows more in the second part than in the first part. Even though it's doubling each time, the later doubles are worth more than the earlier doubles. It's the same thing with our times 3 pattern. It went up by plus 2, It went up by plus 6. It went up by plus 18. It grows by more for the later triples than it does for the earlier triples. And what that means is if you think about one big jump from 1 up to 27, most of that happens in the last little jump from 9 to 27. Now, this is a big, weird idea, so I want you to sit with that. 2/3 of the change came at the end there. There were 3 little purple arrows, and the third arrow accounted for 2/3 of the total change. Okay? Similar sort of idea with my first example. If I do a big arrow from 1 to 4, that's a change of plus 3, and 2/3 of that change happened in the second arrow. You can also notice that the differences between each terms also follows an exponential pattern, and that's kind of a weird idea. So keep those ideas in mind. I'm going to do one other example. Let's say that something doubled, but that it took 10 years for it to double. So let's say we have a situation where let's just come up with a random town. There's a town that's got 10,000 people, and then 10 years later, it's got 20,000 people. So I can write this as a population is 10,000 times 2 raised to the d for a decade. Okay. Now, if I wanted to know what the population was right in the middle, I can do that a couple different ways. I could plug in 0.5 into my equation, or I could take the square root of 2, and I could use that as my growth factor. So what I want to show you is here's what happens when I plug in 0.5. Why is it 0.5? Because that's half of a decade. So when I plug it in, I get that number right there. So let's make this a little bit clearer. This is year 0. This is year 10. I'll put year 5 right here. 14,142. I could have also typed in the square root of 2. Look at the square root of 2 right there. Notice that if you multiply that number by 10,000, you get the exact answer from above. So going halfway is like taking the square root. Okay? Square root of 2 is about 1.4142. What that means is that in 5 years, there was a 41% increase. This from right here, from 10,000 up to 14,000, is a 41% increase. And from here up to here is another 41% increase. But the second 41% increase is worth more than the first 41% increase. It's almost 60% of the growth happens in the second half of the decade. Okay? Another thing I could think about is what if I wanted to know the 1-year growth factor? If I wanted to do the 1-year growth factor, I could do 2 raised to the 1/10th power, or I could do 10,000 times 2 raised to the 1/10th. I want you to look at those two numbers. 1.07. If I go only 1 year, 1.07, 1707, like that. This is a kind of a crazy fact for me that it takes only about 7% increase a year for it to double in 10 years. 7% increase in 1 year doubles in 10 years. A lot of people might think, oh, 7% a year means 70% after 10 years. It's not true, because the 7% in the first year is only 700 people, and the 7% in the next year includes those extra 700 people. And the same thing will happen where most of the change happens at the end. The last year's 7% is so much bigger than the first year's 7%. And that's why instead of 10 years of 7% making 70% growth, it actually makes about 100% growth. So we'll keep working with this idea. I just wanted to give an overview that when the exponent is a fraction, you're getting a number in between, and that you can use a fraction exponent to think of it like a root, and that as exponential growth happens, most of the change happens in the recent amount, even though the percent change is constant throughout. So let me know if you have any questions, and I'm happy